Great.
Also, if you had anything you wanted me to check on, send on see in a couple of weeks.
Oh, yeah. Yeah. Okay.
We've never quite had a project that was, worth justifying. It's not the cost per se. It's that we've never had one specific project.
That was a guess.
And when Scott was, I think Scott Schmidt's going to start doing that. Actually, he was talking to when he was at Corning. He was Corning is, and he was the one who was.
Okay. Looks like people are still. Oh, it's on a cable. I got it. Save that for later. Okay. We'll just give people a few more minutes to stroll in, and then I'll get started. Is this working? Can you tell? It's good? Okay. Okay, let's get started. I'm Kimo Johnson, and I'm from GelSight Inc. Formerly, I was at MIT for about 4 years, first as a postdoc and then as a research scientist. And this technology that we call GelSight is something that I worked on while I was at MIT. It was one of the many projects I did there. And I have to say it was certainly the most exciting project that I did while I was at MIT. And I posted a number of YouTube videos. If you haven't seen them, I recommend browsing our site and checking them out. And those YouTube videos led to a lot of inbound interests. People from a variety of industries saying, we would love to measure this or that, and can you do it with GelSight? And it turns out, as I'll show you in this presentation, that this is truly a platform technology for doing surface measurements. It's agnostic to the surface properties of what you're trying to measure, and that enables us to do very high resolution measurements in a very reliable way. And all of this interest from a variety of industries led me to decide to leave the academic path I was on and start the company to commercialize the technology. And I presented last year at this seminar when the company was just barely off the ground, and now I'm back and I brought some beta hardware with me that we can play with towards the end of this tutorial. And the purpose of this tutorial is just to give you an overview of the technology. So it is very similar to a lot of the material that's on our website. There's a few new images in here in a couple of places, but largely it's to give you, as I said, a good mental picture of what you can do with GelSight. And if you have questions at any time, please just raise your hand or jump in. Feel free to interrupt. We can treat this more as a discussion rather than just me presenting the information to you. So the natural question is, what is GelSight? And GelSight at its core is a very simple system. We have a block of clear rubber we have a thin painted membrane that's a reflective membrane. And when you press an object into the membrane, such as we're showing on this slide, pressing an Oreo cookie in, that painted reflective membrane very closely conforms to the shape of the object that touches it. And as you can see here, the Oreo has been coated with this gold-looking paint. And this might not be obvious what we've done, but we've come up with a way of non-destructively painting the surface of the Oreo. And now our optical system and our computer vision algorithms don't need to know about the material properties of the Oreo. They just need to know about the material properties of the paint that we designed. And so we can use computer vision techniques to measure the surface topography. And here's one of the earliest results. It's a 3D rendering of the surface shown at a novel viewpoint. And this was from sometime in 2008 or so, and this is what initially got us excited and made us push forward on this project. So here's a video showing the elastomeric sensor that we call GelSight. And you can see it's compliant as my finger presses into it. It very closely conforms. And you can also see that by coating the surface, I'm able to reveal a lot of detail that's difficult to see with the naked eye. This is very important for measuring surface geometry. And the natural question is, well, why is it difficult to measure surface geometry in general? And this emery board is an example that I've used a lot, and I like it because it really illustrates how some materials have complex optical properties. If you were to look at this emery board under a microscope, this is what you'd see at fairly low magnification. And I argue that you in fact can't see the surface because the surface is primarily transparent crystals, and the light is propagating into the crystals, reflecting off some spots at angles, creating specular highlights in the image. And there's a lot of complex optical phenomena going on here. And there are machines that can measure this, but they tend to be slow because they have to do fairly fancy tricks to try to get around the fact that the optical properties are complicated. With GelSight, the situation is much simpler. We can just take one of our clear elastomers with a gray reflective skin, press it against the surface of the emery board, and suddenly the image changes completely. It looks like a rocky landscape because that's really what it is. That is the surface structure. And we've removed all of the influence of the transparent crystals from the image. We've non-destructively coated it, and now it's much easier for our visual system to interpret what the surface is, but more importantly, it's much easier for a computer vision algorithm to measure the surface, because now it can be agnostic to the fact that this is an emery board. So that's really the core idea of GelSight. And I brought with me today the box of gel, and we have, I won't pass these around because they're somewhat delicate, but we have these pieces of gel, and they go on this beta system over here, and we can play with it after. You'll see that you just put a sample in, put the piece of gel on, and you can get nice, beautiful surface images like this, and we can also get 3D surface measurements at high resolution. Yep?
This is probably coming up, but can you peel it back off?
Yes, yep. We can peel it back off. So we've only coated the surface with the paint for the time that it's in contact, and then you can remove it. You can even reuse it again if it doesn't get cut or damaged by the sample that you're using.
Stretch it out or something so it uses that surface, or is it just like...
So I'll talk a bit about the materials. We have a very wide range of materials that we can use for this, and some of them are very delicate and fragile, can only be used once. Some of them are very rugged, can be used over and over again. And it depends on the properties of the surface that you need to image and the imaging conditions too. We'll get into that. So here's the tutorial outline, and I'll talk a bit about the history of GelSight, how this idea came up. It was the idea of my postdoctoral advisor, Ted Adelson. And then I'll talk about the core components of the system, the gel in particular, the reflective pigments, and also the imaging algorithms that we've developed. I have a gallery of surfaces and skin images that we've done using GelSight, and we are continually adding to this gallery when people send us new materials to image. And then I'll describe some of the systems and prototypes we've built, and then also describe this system, and we can do the demo. The original motivation for GelSight is really quite interesting, in the sense that it wasn't developed as an imaging technology. It was developed as a tactile sensing technology. And my postdoctoral advisor, Ted, he and his wife had children within the last 10 years, and he's a computer vision and human vision scientist. He thought he would be fascinated to watch his children's vision develop, because you can see them not understanding the world to developing an understanding of the world. But in fact, he was surprised to learn that for infants, the sense of touch is available day one, and vision is not. And so he was fascinated by the fact that touch was incredibly important to children and to infants. And so he thought, like the natural MIT professor, how could we make a robot do this? And he started asking his colleagues in the Department of Brain and Cognitive Science what was known about touch, human touch. And most of them said, well, nothing is understood because we don't have a sensor that can measure touch in the way that's similar to human skin. We have touch-sensitive devices like the iPhone or this trackpad, but these are really nothing like skin. They're rigid surfaces. They're actually very low resolution in that they can detect when a finger touches it, but they can't see much of the detail of what's touching. And so there were really no good sensors, and no one had started to do research on human touch. And so he thought about it, and, well, as I said, he looked at a lot of the technologies for touch sensing out there, but they're really not anything like skin. And in some ways, nothing matches human skin. In terms of resolution, I mean, when we're sensing a surface with our finger, it's an active sensation, but we're able to feel surface roughnesses that are quite remarkable, considering the density of sensors in our fingertip. We're very sensitive to small forces, and the unique property of skin is that it's compliant. Our skin will deform when we're touching an object, and that's important to how we sense the object. So he started thinking, well, how can I make a deformable sensor? And then the second thought was, how could he put a camera inside the skin? Because being a vision scientist, he thought, if I can turn touch into an image, then we can apply all the tricks in the book that we know for doing computer vision and imaging, image processing, and maybe that's one way of making a touch sensor. First, turn it into an image, and then do an image processing pipeline. And that was the initial idea. So take a slab of clear rubber and put a reflective skin on it. And then when you press into it, that reflective skin will deform based on touch. And putting a camera on the other side, you can look at that deformation, and now you've turned touch into an image. And as I said, this was originally designed to be a robotic fingertip, and this is a simple prototype that we made. It's got a camera inside here, a curved piece of this gel with a reflective skin. And you could imagine mounting this on the end of a robot hand, and you can go around and touch things with it. And in fact, there's still an ongoing project in the lab to miniaturize this and to try to understand touch. But within the first few months of my postdoc, he brought in this material and showed it to me and asked if I thought we could measure 3D using it. And that is really what spun off into the technology as it is today, which is a very high resolution 3D measurement system. So now I'll dive into the core components of a GelSight system. In particular, at the heart is the elastomer that we use. And we really don't have any magic elastomer at this point. We're using a lot of off-the-shelf materials that we melt down and mix in some other ingredients to our own recipes to change their properties. But fundamentally, we just need a clear, soft, durable, elastic rubber or elastomer. We've used silicones and polyurethanes. Thermoplastic elastomers are one of these rubbers that's everywhere, but people don't know it by name. And that one works quite well. We've also used gelatin. it really serves as just a clear substrate for holding that reflective skin. And it doesn't need to do more than that at this point. A lot of these can be formed in a dish or heated and molded. There's many ways of making it. Sometimes we make them in sheets and we cut out samples like the circles you see here. But some of the earliest were done, as you see here. Just stick it in the oven, melt it down into a shape, like a circular disc, and then put a reflective coating on it. At this point, the reflective coating is really the secret sauce that we've developed. And intuitively, if you just took this block of clear rubber and you spray painted it, well, that might create a nice looking surface, but then as soon as you touched it, that paint would probably crack and break and maybe even flake off. And the key properties that we need are an elastic, opaque, and thin coating. We don't want this reflective coating to be too thick, because then it will act like a blanket and it will cover the surface and you won't be able to see the very high resolution details. But you really need a stretchy, reflective, opaque coating. And we've come up with a variety of ways of making that kind of coating. Some of them are published in our papers. For example, one simple method just uses these reflective pigments that we put into a binder that's made out of the same material as the base gel. So if we're using thermoplastic elastomer, we take some of that TPE, melt it down in a solvent, mix in the pigments, and then we have an elastic paint which we can airbrush on the surface. And we have a variety of other methods for making these kinds of sensors. Now, there is a connection between the reflective characteristics that we use and the imaging algorithms. And in our current systems, we prefer the reflective coating to be matte or diffuse, so it doesn't have strong specular reflections. And that matches very well with the algorithm that we're using for the 3D measurement. However, the core idea is that we control the reflection, or control the reflective properties of the surface. So we could, in fact, use really any reflective properties as long as it's well understood and we can model it well with our software. So there are some advantages to having shiny surfaces, though we would need to use different imaging algorithms to measure the surface. So, over the last 4 years, we've done a lot of work on exploring the space of GelSight configurations. For example, we've used elastomers that vary from soft to hard, and you can get very interesting measurements of very different kinds of structures in that way. We've used sensors that have been very thin to very thick. As I said, the paint can be diffuse. That's what we prefer now. However, it could also be specular, and there are some advantages. We can make the sensor into a variety of shapes, so it's not limited to being a flat piece of gel like we see here. If your object has different curvatures, we could make the gel with that curvature so that it conforms better. And it can also be made into a very compact device, and we'll show an alpha prototype at the end of this presentation. With a hard elastomer, we can measure pressures of a car on top of the gel. So this is a tire tread from a car, and Professor Adelson literally bought one of these ramps you use to change the oil of your car, cut a hole out of the top, put a big piece of acrylic and then a piece of very hard GelSight material on it, drove his car up on top of it and took a picture, or took a video actually. And if you were a tire manufacturer, you might want to understand tread wear. This could be a way of measuring tread wear while the tire is still on the car. So that's one end of the spectrum. A lot of pressure from a full car. In this experiment, we have a bubble, or a container with soap bubbles, and on the other side of the container is some very soft GelSight material, and you can see that the pressure from the soap bubbles is enough to deform the elastomer. So this was an incredibly soft piece of gel, very fragile and delicate, but maybe there's a connection between the efficacy of detergents and the structure of the soap bubbles. And perhaps if you were making detergents or foams, you might be interested in soap bubble topography. So this could be one way of measuring it. Now, as I've presented GelSight to a lot of people at various conferences and also had lots of discussions with people who send me images, people have compared this to scanning electron microscopy. And that's been very interesting to me because I had been focused for a long time on just doing measurements, doing 3D measurements of surfaces, trying to get the 3D to be accurate. But a lot of people have said, look, when we put a sample in an SEM, most of the time we just want to see an image of the surface. And I've talked to people who do imaging of lotus leaves to try to understand hydrophobicity, and those have features on the scale of what we can do with GelSight. Yet GelSight is significantly simpler in the sense that it's non-destructive. We don't have to coat it with gold, and it doesn't have to be done in a vacuum. As you'll see, we can just stick a piece of gel on a sample and get images that are SEM-like in literally seconds. So that's been interesting to me to learn that, in fact, just seeing a surface in this way has value already. We don't need to do the measurement. And that's really where this gallery comes out. It's a lot of cool images done using GelSight, and this is not 3D. It's just taking the gel, pressing it in, and taking a picture. So the first one that we have here is an oregano leaf. And if you look close up, or even closer, we can see a lot of interesting structures on the leaf. These hair-like particles, different glands. And again, this was done in a pretty simple way, pressing gel and taking a picture. In fact, some of these images, like this one, was done with an iPhone camera. So this is Professor Adelson's finger with a piece of gel. And then with an iPhone camera, we can already see skin detail that is really beyond what a lot of people can do today in vivo. So the natural question is, why does it give such a 3D appearance? Well, the gel itself is viscoelastic, so it flows around surface, fills in the holes, and that is actually surprising to us. Not all the gels that we use behave that way, but the ones I'm showing for the skin images really do flow around the structures, like the hairs, coat the surface very well, and in fact you can't really see the gel, which is surprising. So the result is that we're really coating the specimen with a thin layer of this elastic paint. And we can get images that no one has ever really seen before. And people at cosmetics companies who do research on skin have validated that really we're seeing features in vivo that are very hard to see. So this is again a striking image because you don't see the gel. You might expect the gel to behave like a tent and like flow over, and you'd see some kind of structures, but it really doesn't seem to be there at all.
See shadows.
And we can see shadows.
See projected shadows with light underneath.
Exactly. Yep. And that's also what contributes to the real 3D appearance, because our visual system is very good at interpreting shaded images like this with simple reflective properties. And this is why there's value in just seeing GelSight images for people who want to see features. And this was annotated by someone who knows a lot about skin, and they said they were really impressed to see what they call canyons and different glyph lines. And I don't know the medical or research value to these kinds of things, but people in the field were very excited about this. Some more skin images. My wife was a volunteer for this, or a subject I should say, and this is a spot of skin on her leg. It's a spot of dry skin. And this was a pretty simple experiment where we did a before and after before and after using moisturizing lotion. And so this is the before, and then this is the after. And if you were a moisturizer company, perhaps this has a lot of value. You can see quantitative changes in the skin. And in fact, I can flip back and forth. You can see a lot of this dry skin, perhaps has been rubbed away through the process of putting the moisturizer on. And you could perhaps learn a lot about what the moisturizer is doing. In fact, this image is very high resolution, and you can see some drops of moisturizer still on the skin. And then I like this image a lot. This is an image of my stubble after, a few days of not shaving, and it's it's really, really striking how we can see the hairs. And do we have a DVI? Is that what this is?
Yeah, it's about that. We'll try to proceed while you're talking without disrupting too much.
Well, we could just save it for the end because there might be some setup time. It's for this system, for when I do the demo? Yeah.
Okay. So proceed and ignore the maybe in the group.
Okay. So, in fact, with my stubble, you can see the fact that I shave with a razor, so they're cut off at a nice clean angle. If I were to shave with an electric, in fact, I should do a side-by-side. It would be interesting. I think it shreds the ends of the hairs when you use an electric. But with a razor, you get very clean cuts. We've thought of doing experiments where we wear a piece of GelSight on our face for a whole day and then make these measurements time-lapse. And then you can see the stubble growing out over time. And there's probably not a lot of value in that, but it would be kind of cool. Many surfaces in nature have very interesting topography. And I mentioned the lotus leaf, and that's been of interest to scientists to try to make coatings that behave like a lotus leaf, for the watersheds. This is a sand dollar, and it has, again, very, very interesting structures here. This is a dramatic example of how some materials have beautiful optical properties that would be disastrous for a 3D imaging algorithm. I mean, if you were to measure the surface structure of this peacock feather, you would have to understand all of these specular highlights, and you'd have to learn to ignore those, because specular highlights tend to be noise in a lot of imaging algorithms. And if you just want to measure the structure, the GelSight image is significantly easier because we filter out all of those properties in a direct and simple way. This is an image of a chicken feather, and we can see multiple levels of resolution. And this is an image that some people have compared to scanning electron microscopy. And it's really not done at very high resolution, but the fact that we've coated the surface with a diffuse pigment like this and taken a picture reminds people of that, and it's done in a simple way. And finally, a lot of engineered materials have surface topography or surface structures that are very directly related to their function. And this example shows a Post-it note. And you can see the paper fibers of the Post-it note. You can also see discrete glue droplets. And the distribution of glue droplets and the fact that they have different sizes tells you a lot about how a Post-it note works. The fact that it's only adheres weakly to a surface, because as you press it down, perhaps some of the bigger drops burst first, and then there's still some remaining smaller ones for the next time you pick it up and put it down. So this is something we've encountered as we've talked to a lot of people at different companies. The fact that today coatings and materials are often engineered with surface properties that directly relate to how the surface functions. You can think of the Post-it note, but also abrasives come to mind. Sandpapers, coatings for ships and other things. There's all sorts of work going into engineering microscale topography. And GelSight provides a universal way of measuring that. Any questions so far? Yep.
Have you looked at a perfectly smooth surface, like an optical flat or something, just to make sure that the details that you're seeing are not from the GelSight material itself?
I haven't done that lately, but it is true that first you have to start with a fresh, clean piece of gel if you want to get a clean measurement. This is a tacky material. It will pick up lint, so if you don't have a clean environment, and even as we'll see today, I'm not using a fresh piece of gel and this environment isn't particularly clean, so there are things stuck to the gel that do get imaged. So there is that issue. But in principle, if you start with a clean piece of gel, the features that are on here are small compared to the features you might be interested in measuring. The pigment size that we're using is on the order of 500 nanometers. So that's average particle size. And that's also fairly well matched to the optics that we're using right now, so in the sense that the particle size is smaller than the optical resolution of that camera. So we're not seeing individual particles, or pigment particles. Does that answer?
Yeah, and so any, assuming there is a roughness to the layer of the pigments or the material,
Yeah.
that's not as critical, I'm assuming, because once you press it down onto the material you're looking at, that flows around.
That's right. It flows around. I mean, in our current system, a lot of these are made through a manual process, so there can be pigment clumps that are larger than the pigment size. And as we ramp up production and bring in contract manufacturers to make this, we expect those quality issues to change. So in a lot of these current ones, you might see a clump of pigments, but it's fairly sparse, and you can identify them easily. We have measured a piece of our gel in an SEM, and it is interesting to see the nanoscale surface roughness and things like this. But it is at a scale that's beyond what we're measuring today. So, yeah. Any other questions? Okay. So let me describe the original GelSight system, because that gives a good idea of how our algorithms work and how the optics and illumination all work together to get 3D measurements. And I'll kind of go quickly through this and get on to some of the later technical details. But all of these details that I'm describing are essentially what's in the beta hardware here. We've made a nicer version of it, one that's easier to use than the prototypes I built at MIT. We've improved the algorithm somewhat over the papers that we've published, but in a sense, it's really conceptually the same thing. So at its core, we have a system that uses a single camera and multiple lights to measure 3D. So there are lots of ways to measure 3D structures that come out of computer vision or machine vision literature. And in fact, we could use almost any of them, because fundamentally, when you press a piece of gel into the surface and you remove its optical properties, you can use any kind of machine vision at this point. Structured light, you could do laser scanning, you could do multi-view 3D measurements with multiple cameras. The one we've chosen for a lot of what we do here is a single view, multiple light source approach called Photometric Stereo. It has advantages for measuring very fine scale surface features. Literally, you get a measurement at every single pixel in the image, and when you have an 18 megapixel camera, that gives you a lot of surface detail. So the simplest system was this prototype that I built back in 2009, single camera and 3 lights. And these are colored lights, red, green, and blue. And I'll get into why that works and why we did that. So why 3 lights? Well, if we didn't have 3 lights, if we only had 1 light source, we would have to solve a classic computer vision problem called shape from shading. And this is a problem that is well known to be hard. There's a professor at MIT who posed the problem back in 1970 for his PhD dissertation. And after more than 40 years of work, it's still basically unsolved. And the reason it's unsolved is because it's really fundamentally challenging. It assumes you have some shaded image from a single, in the simplest instantiation, you have a single light source and you have a surface or an object that's being illuminated by that light source. So you've made assumptions that the lighting is simple. You often make assumptions that the surface reflectance properties are simple. Lambertian is the term used in literature, but it just means diffuse or matte. And so let's suppose we have that kind of imaging scenario. The shape from shading system would take an image like that, run it through the magic shape from shading box, and output some representation of the shape. And this is fundamentally challenging because let's suppose we have the simplest possible shape, perhaps a sphere with a single light source. This is what you'd see with a shaded image. And so the light is coming from this direction. the shape from shading algorithm needs to analyze the image, take shaded image values or shaded intensity values, and determine what the local surface shape is. So let's suppose you're this algorithm and you're running across the surface and you encounter an intensity of 0.8 somewhere here. Well, how do you map 0.8 back to something that has to do with the surface? Well, it's challenging because, in fact, all of the points on these curves have the same intensity. So if you're at 0.8 and you're on this curve, all of these points have an intensity of 0.8 because all of these have surface orientations that make the same angle with respect to the light source. And it's that angle that determines the intensity in the image. So it's fundamentally ambiguous. If you encounter that 0.8 intensity value, you can't know where you are on that whole circle. It could be any of those orientations. And so you really don't know that much about this shape. There's still, at least in theory, an infinite number of orientations that you could be. You've constrained it down to be on a circle from being the entire sphere, perhaps. But that's not enough. And that fundamental ambiguity makes shape from shading a very hard problem to solve with a single light. However, if you give yourself more than one light direction, and this was discovered by Woodham in 1980, in particular, let's suppose instead of this single sphere lit from one light direction, we have the sphere again lit with 3 lights, and I'm showing the 3 lights as different colors so they're easier to see. So we have a red light from this direction, a blue light from the bottom, and a green light from the upper right. Well, with respect to each of those light directions, we still have that fundamental ambiguity. However, that ambiguity is oriented with respect to that light direction. So you can see these curves, which are called isophotes, which are locally ambiguous with respect to one light, but now when you take them with respect to 3 lights, they intersect. And in fact, the triple of values, let's suppose you observed 0.8 in red, 0.6 in green, and 0.5 in blue, that triple has a unique intersection point on the surface. So you can uniquely identify the surface orientation based on that color triple. And that's the fundamental idea of photometric stereo, is now you have the same surface, but you light it from different directions. And those different intensity values, when taken together, can uniquely identify the surface orientation. Here's a concrete example. Here's the Oreo pressed into our GelSight sensor with red, green, and blue lights from different directions. And the reason we're using red, green, and blue lights is because common cameras have red, green, and blue filters in them to get, it's called a Bayer mosaic. So those, if you take those independent color channels and you just look at them, they look like grayscale shaded images from different directions. And so that's the trick. We've multiplexed different light directions across color. And we can get 3 light directions in a single color image. And that's advantageous because now we can do video rate 3D measurements. And the first system that I built using this technique was a real-time surface reconstruction system using a color video camera and our reconstruction algorithm. So to get the 3D, we calibrate the system. And here's one of the earliest calibration targets we built. It's a grid of spheres. And in fact, we still calibrate the same way. We have targets of a variety of shapes and sizes depending on the imaging scale you need to measure. Over there, I actually calibrated with a ball grid array because for doing very high resolution measurement. But fundamentally, you can build a direct mapping from color to surface orientation. And intuitively, this is how it works. You take a picture of the calibration target pressed into the sensor with the illumination. I'm showing red, green, and blue lights here, 3-channel photometric stereo. And color maps to orientation. So if you observed a green pixel in your image, you know that green pixels only come from surface orientations like this. And you can see that based on the calibration target. If in the image you observe a red pixel, well, it can only come from surface orientations like that. Blue can only come from surface orientations down like this. And mixtures of color, various amounts of red, green, and blue, can only come from where you've observed them on the surface of the calibration target. So you can build a lookup table that stores RGB triples and maps them back to surface orientation. And that's what we did in the first system. Intuitively, if you observe the color 10, 200, 3, let's suppose it's 8-bit color intensity values, you can look that up in your table and you can get surface gradient, perhaps 0, negative 0.3. That's a local representation of surface slope. And then for an alternative color somewhere else, you've observed 200, 10, 3, and you go to your lookup table, you get a surface gradient of 0.2, 0.2. And you can convert a color image at this point very quickly into an image of surface gradients just through direct lookup. And once you have surface gradients, you're one step away from having the surface, because the gradients are derivatives of the surface. And we can use a surface reconstruction technique that integrates those derivatives to obtain the surface. And mathematically, we have surface gradients P and Q that we've obtained from our lookup table. Those are done through calibration and through the lookup process. And what we want to find is a surface Z, which is some function of x and y, some function f, where the partial of f with respect to x should be as close as possible to the P gradient. The partial of f with respect to y should be as close as possible to the Q gradient. You can set up this system, it's a quadratic system, and solve it for the best surface that optimizes for the gradients that you've observed. In the literature, it's known as solving the Poisson equation, and there's lots of work on how to solve this quickly, robustly, etc. So it's fairly standard practice. And at the end, after you've integrated your gradients, you have your surface in very high resolution. So here are some examples of objects that might be challenging to measure using optical techniques. For example, this is a trinket with some metal outside and a very clear glass inside with this angelic face. Pressed into GelSight, you can see, with red, green, and blue lights, you see an image like this. And then using our lookup table and then integration process, we can get 3D measurements like this. And these are actually some very early results, but they illustrate the point. Again, objects that might be challenging to measure using some techniques. This is a scratched metal with different albedo changes, different paint on it. And we can get nice 3D measurements of the surface of that. It's a drawer pull, surface of the drawer pull. And as I said,
It's a novel system.
you get to hear me live. You don't have to listen to the video. So we've seen a lot of these, but I'll show the real-time system. This is the earliest YouTube video that we put online a couple years ago. And it shows this system that I built that uses RGB photometric stereo at 30 frames per second. Again, big box at that time. But people had a lot of fun playing with this. It was like a science fair. You go up, you press your finger in, you see real time your fingerprint. So this is what the camera sees with red, green, and blue illumination. And in real time, we can convert that into a surface. And now we've rendered the surface. You can spin the rendering around. You can change the light direction. And even this initial system had fairly good resolution. So this is perhaps, what your teeth feel when you brush them. It's a toothbrush. You can even see a lot of the bristles moving. The Oreo cookie made an appearance. And this system is still in the labs at MIT. It still works. People like to play with it. So there are some cookie crumbs on the sensor, and you can see the detail of my fingerprint and also the crumbs rolling underneath my fingerprint. This is Ted Adelson's pulse. So just pressing his wrist against the gel was enough to conform it. You can also see a lot of interesting skin detail. And then finally, a result that shows the resolution capabilities of the first system. This is a $100 bill. And the raised printing of the bill is enough to, it deforms the gel enough that we can see that raised printing, even in real time. So that system, I took that around to a bunch of computer vision conferences a few years ago. It won Best Demo. at CVPR, which is the top conference in computer vision. People really liked playing with it, but the number one question at the time was, what can you do with this? And in fact, we didn't know, because we weren't aware of surface metrology and people who study surfaces. This, doing computer vision, we certainly knew about the kinds of tasks of measuring objects and 3D measurement of things like that, but we hadn't really learned that there's a field of people interested in measuring 3D structure of surfaces. So we didn't really know, and people started telling us what we could do with it. So this system works on any material because of the GelSight properties. We used a single color image at that time, which led to real-time capture. We could do 30 frames per second surface reconstructions. But the original system was a fairly bulky device, and the optical resolution was perhaps around 20 microns for a variety of reasons. And after we published that paper, just for purely scientific reasons, we thought, how can we improve the resolution? What's preventing ultra-high resolution? And that's what led us, a few more years into the system that you see today. And there were a lot of engineering improvements. Really, all aspects of the system were re-engineered. But one of the key observations we made was, in fact, the way we made this GelSight sensor was limiting our resolution. We needed to find and use much smaller paint particles so that we're no longer looking at the paint themselves, those particles themselves. We had to improve the reconstruction algorithm so that RGB photometric stereo with 3 lights was nice for a real-time demo, but there really aren't enough constraints to deal with all of the other kinds of phenomena you might observe in images, such as shadows, such as strong depth discontinuities. It helps to have more than 3 images so that you can determine, or you can be robust to a lot of other situations. So we re-engineered the gel itself. We re-engineered the optics and the illumination and also the algorithms. And we were able to get a 10x spatial increase in resolution in each dimension. So with the system here today, we're imaging into the single-digit microns. So perhaps we can resolve features around 3 to 4 microns in that range. The camera pixels themselves at the highest magnification with that lens are sampling the surface at about 0.9 microns per pixel. But due to the resolution of that lens and also due to the Bayer mosaic, Nyquist's theorem would tell us that we could potentially resolve 2 micron features, but it's probably more like 4 microns once you account for some of the filtering that goes on. So that leads us to the later improvements that ended up in a paper we published last year, but also ended up directly in the system over here. One of the most dramatic improvements is simply improving the GelSight sensor itself. And here is the nose. I believe it's from a US dime. And our original system used a metal flake pigment that we made a reflective paint out of, as I described. You take some of those metal flakes, you mix them into some of the base material as a binder, and you airbrush it on. But those flakes were around 20 microns in size, and they act like little mirrors when they're embedded in that surface. And if you zoom in and look at it with even modest magnifications, you can see a lot of texture due to those metal flakes being at random orientations. And that texture would be measured because that's what you're seeing, right? And so this gets at the question of, what are we really seeing? Are we seeing the surface of the gel itself, or are we seeing the surface of the sample you want to measure? When we're using metal flake pigments at 20 micron flake size, you really are seeing a lot of the texture due to the gel itself. However, when we replace those metal flake pigments with silver microspheres, average particle size 500 nanometers, you no longer see them. And so we can get a much cleaner image here. And it's because that particle size is smaller than the pixel size of our camera, or what we're resolving. So that was a simple hardware change. Yep.
What's the smallest microsphere that I've tried?
We've tried so we have some that are down at 200 nanometers, and it could be that if we just put this whole system on a microscope rather than on this SLR setup, we might be able to see a difference, but we can't see a difference with this setup. Yeah. I believe there's...
Surface metrology background, people who would want to consider it smaller than 500 nanometers.
So I think to measure features smaller than that, we need to be doing something other than what we're doing now. This is fundamentally an optical system, right? So we're diffraction limited and such. So, you could perhaps combine GelSight ideas with some other imaging technology, but currently our system's focused on imaging micron scale features and up.
Depth resolution, you have a simple descriptor for that, for the height resolution you can resolve?
All I have are some results on calibration targets, which we've had for a while. We have some thoughts on how we can quantify depth resolution, but it's not, we don't directly measure depth, so it's, we'll get to that.
Well, one of the things, a profilometer typically has a 2, 5, or 10 micron radius tip. So, we're 10x below the finest tip in terms of the 200 nanometer spheres.
Yeah, and in fact, that is a good point. The fact that when I'm talking about resolution, at least at this point, I'm really referring to spatial resolution, right? And our Z resolution is considerably finer than our spatial resolution. So we're sampling the surface at about a micron per pixel, but we get local estimates of surface orientation at each of those. We integrate those into a surface, and you'll see on some of the calibration targets that I've done, we get smooth, continuous surfaces that show, nanometer, certainly submicron level Z resolution. So there really are two resolutions, and a lot of instruments also break it up that way: Z resolution versus spatial resolution. So when I talk about being able to resolve features, I'm talking about spatially features on the order of perhaps 4 microns, something like that. Silver microspheres improved quite a bit, but they have a unique reflectance characteristic that wasn't compatible with our illumination from our original prototype. So we had to redesign the illumination, and this is the design that appears in the beta hardware. And the key is to bring the light in from the side and use the glass plate as a light guide, in a sense. And if you come up after and look at what happens when we have a sample under here and we have the gel, you'll see that you get very strong coupling of the light coming right through the gel and right onto the sample. And you can get really beautiful images using this technique. So we move the lights right onto the side of the glass plate, and then the GelSight sensor here just gets stuck on the glass right now. So some of the algorithmic challenges we had to account for or spatially varying illumination. We can no longer make all of the nice assumptions that people make in computer vision literature, such as the camera is at infinity, the lights are at infinity. If you want to make accurate images, you have to try to model really what it is. We don't have lights infinitely far away. The lights are in fact only a few inches away from the sample. And the camera has a realistic field of view. It's not an orthographic camera. We had to model all of those things in our software to get more accurate results. We also had to account for shadows. This is an image of a Greek coin provided to me by a numismatist at Princeton. He has a whole collection of these coins, and they want to understand how each of these features in a set of 100 coins relates to one another, because that helps determine the order in which these coins were made. So these are things that you never know about until people approach you and hand you these coins and explain their measurement problems to you. And this was a very interesting project. And these coins are made by striking a die. I think it's from, I had the date on, I think on another slide. But as you strike it, those features will spread out over time. And at some point, the top or the bottom die needs to be replaced because it wears out. And so by analyzing the surface features and how they flow from one coin to the next, they can get an ordering of the coins, and they can also determine which coins belong to which dies. And this particular coin set of 100 coins, I guess in that field, somebody will spend 5 years analyzing these things under a microscope, annotating them, and doing a lot of work to determine where these features are and come up with a hypothesis of how they're ordered. And all of that work is enough to get a PhD. It's very interesting to find out what other people do for their PhDs. We're involved in a project with them where, in fact, we're doing quantitative surface measurements and using computer vision algorithms to find the features and track them. And hopefully we don't find something that's distinctly different from someone who's published a PhD on this, because then, of course, you get into some heated argument over, is the algorithm right, or is this person's 5 years of work correct? But certainly interesting to know what people want to do with measurement technologies. In any case, we had to do a more accurate measurement of the illumination. I won't go into too much of the mathematics here, but the simple illumination model that most people assume when they're doing shape from shading or photometric stereo techniques is this part of the equation. A simple inner product of a light direction with a surface normal, perhaps some ambient illumination modeled by this constant C. And that illumination is correct if your light is infinitely far away, if your surface is perfectly Lambertian, and if, in fact, you're only talking about surface normals that are within 90 degrees of the light direction. So there's a lot of ifs there, which means to say that in practice, this model really isn't correct. I mean, it's not very close. And people deal with it typically by using tens or even hundreds of light directions. And when you over-constrain it that much, you can get accurate surface measurements using this simple linear model. But 100 measurements takes a long time. It's a lot of data. What we've done is we've added a quadratic term to the equation, which is able to model a lot of the actual characteristics. The fact that the lights are closer than infinity, the fact that we're talking about a surface that's diffuse but not perfectly Lambertian. And there's some theoretical results too that show that you really only need a quadratic model if your surface is diffuse. A diffuse reflectance function acts like a low-pass filter, and so really any lighting environment can be modeled quite well with just quadratic approximation. But this additional term means we need to do a nonlinear optimization, and things get a little bit messy. However, luckily for people who use our systems, it's all in the box. So we've just implemented the algorithms that we need, and we're able to get high-quality surface measurements that also handle shadows by having extra illumination conditions. What I haven't mentioned is, in fact, our beta prototype here and a lot of the prototypes we've built use 6 light directions instead of 3. There's nothing magic about the number 6 other than the fact that it's greater than 3. But we use the extra illumination conditions to reject shadows. And you can see the result of our optimization shows that on this particular channel, when the light is coming from this direction, the algorithm has learned to ignore the contributions from these pixels because they're biased by shadow. And when the light's from different directions, it'll learn to ignore the contributions from those other directions. Now, if in fact there's a small concave region of the surface that, like a pit, that is in shadow from all 6 light directions, we have smoothness constraints that smooth in those pits. And that's one area. In fact, with the current lighting setup, it's not common that we encounter those. But there is one result in this slide where I can point that out. I'll skip through some of the details. Here's the early prototype. It's gotten a bit nicer. Originally I had a set of 6 light switches, and I'm switching lights on and off to get the different light directions. Pretty clunky, but this is what you do to get a paper, at least to do the research to prove that it works. And here's some of the early results. This is a dime under a piece of gel. So this is a microscope slide, a piece of gel that we've made that's attached to the slide, and the gel is pressed up against the dime. A rendering of the 3D surface that we measured. And I'll show a lot of renderings like this where I take the surface topography and I shade it with a single light source and diffuse reflectance. And you can see with this setup, we've been able to capture a lot of very fine scale features on the dime. Actually, let me skip this validation because I'll go into this one. This is a Rubert specimen. It's a periodic sinusoidal target, period of 100 microns and a height of 3 microns. So this is in fact compressed this way, this plot. We have 3 microns here on the y-axis and a millimeter across the x-axis. And this is what I was suggesting before, how the fact that we have local surface orientation measurements very finely spaced, and when we integrate them, we can get a smooth curve that shows submicron Z resolution. Because we're not stepping through Z to measure it, we're integrating lots of local orientation measurements. So what I plotted here is our measured surface, and this is a scan line out of the center of the image. We in fact measure, of course, the whole surface. And I took a scan line out, and then in the red dash curve is an analytic sinusoid plotted with the same parameters that the manufacturer said.
But it's not an independent profilometer, it's not an independent...
No.
It is just a sinusoid.
That's right, it's a pure sinusoid.
Yeah.
And it would be interesting to get independent measurements of this same sample from a lot of different measurement technologies and see. I mean, the fact that our measurement agrees quite well with a pure sinusoid suggests that in fact their manufacturing techniques are reasonable for manufacturing the specimen. But again, this is a scan line. It would also be interesting to see, are there any defects on this sample, and we could do more thorough analysis. Here's another sample. It's a 19 micron and 135 micron in period. And again, it's fairly smooth at this scale. So just some visual results of why it's important to handle shadows. And this is the Greek coin again. If we put that Greek coin on our original real-time system, you would see these kinds of defects because a shadow is very dark. When you go into the lookup table, try to look up that dark value, it usually gets an erroneous measurement at that point, and then you integrate it in and you get distortions on the surface. With more light directions, we're able to determine which pixels are in shadow and then get a much more accurate measurement of the surface of the coin. We also have this image and video showing a resolution improvement. So in our first paper published at Computer Vision Pattern Recognition 2009, we had this result of a $20 bill, the raised printing, and people thought, wow, that's really amazing. And it was shown at this resolution. And it was. The fact that you could see raised printing using this technique was quite impressive because in the field, what people would typically do to measure surfaces might be laser scanning, structured light. I really don't expect any of those will see the raised printing of a bill because the light passes right through the bill. It would be very hard to see that. So we could see it. But when you zoomed in on that result, you see, in fact, that we don't have the resolution to really resolve a lot of detail for the reasons I mentioned in the presentation. One, the size of the paint particles we were using, and also the limitations of the optical system. With our improvements in the latest paper, we're really able to see a lot of the detail, the fine grains, the fibers of the bill, the raised printing, and this is the surface in our 3D renderer. It's just a little 2 millimeter square piece from the word treasurer, the TR. And we had a hard time convincing reviewers that the resolution was really impressive. Maybe they're not used to seeing things on this scale. So we did this example where we laser printed the word ink on a piece of clay-coated paper, and then we do a flyover of the word ink. And you can see the raised printing, so the accumulation of toner particles on the page. Individual toner particles, I believe, are on the order of 10 micron or tens of microns. And I think that's just another resolution example. In fact, this system goes even higher resolution than these results. And this was presented to a computer graphics community because of the fact that it's a universal method for measuring surface topography or surface geometry. And this is useful for graphics. A lot of the improvements in realism over the last decade in computer graphics and in the movie industry comes from the fact that we can measure things very accurately. You probably have all seen motion capture systems where there are multiple cameras and outfits with little lights all over them because they want to measure the motion of a subject to animate a figure in a movie. But equally, measuring illumination for accurate rendering has been very important, and also measuring material properties like skin topography or measuring really any surface. A friend of mine who has experience working in that industry says that a lot of times artists are drawing what they believe tree bark should look like or what they believe any of these materials should look like, and to have a universal system for just directly measuring that could really improve their workflow. So that's why we published there initially. And you can see renderings and also inset color photographs of a variety of materials, such as leathers, plastics, cork, wood, and some machined metals. Now, we've also come to appreciate more recently that there are applications of GelSight in the emerging 3D printing industry. And it's probably not obvious, but there are textures all around us, such as the wall coverings, the vinyl in your car, fake leather in a handbag. A lot of these are manufactured materials that are made to look like something real, and made to look like fancy leather or fancy wood, artificial wood grain. And there are 3D printers out there where they're just making measurements of surfaces and printing them out for a variety of industries. And we found that GelSight is a very good match for that kind of technology. And finally, just a 3D result of one of the skin measurements showing a lot of these canyons that people are interested in. And one final thing is that we can, with this system, we can take a color photograph and we can stitch that on top of the measurement to get a very compelling 3D rendering of an object like a coin. So we have both the geometry and the color photograph. And we've thought of applications for coin collectors, having digital 3D galleries of their coins and things like this. We don't know what the value would be, but there could be. The coin collecting and trading industry is actually quite large. One final example, forensic ballistics. We've been approached by some government organizations and police departments with this interesting problem, which is how do you fingerprint cartridge cases or bullets? And today, this is done in a comparison microscope where you might have a cartridge case that you collected at a crime scene, and you put that in a comparison microscope. You have one that was fired through a gun, perhaps that you obtained through search warrant. You put that again, and then you, by eye, compare the features. You look for different kinds of striated marks, different textures. But it's, the people who do this have been trained to look for these features, but it really is subjective. They're saying, well, I see 9 matching features, it must be the same gun. What we can do is actually make a 3D measurement of the surface and obtain a very high resolution detailed map. And we have all of this as quantitative data. So now you could go in and really make a very accurate surface matching, and using cross-correlation techniques, using more advanced feature matching techniques out of computer vision. And we have some grant money from different government organizations exactly for that reason, to try to take our measurements, combine them with advanced machine learning, and see if we can really improve the state of the art in that field. Finally, a few slides on surface roughness measurements. When people started approaching us, asking us if this could be used as a surface roughness tool, or what our capabilities were in that space, somebody suggested very early on that we buy a surface roughness gauge and do some sample measurements of it. So that's what we did on these slides. This is 1 millimeter, 1 millimeter square from this grinding 0.8 micron RA patch, a false color rendering of the surface. Here's grinding compared to vertical milling, and you can certainly see the difference in surface topography. These are depth images, so bright pixels are high and dark pixels are low in depth, but the false color rendering is easier to interpret. We also did a bunch of roughness measurements over different areas on those patches, and they form a distribution. This was not a very high quality surface roughness gauge, so I really don't believe at every location of it it's very close to its nominal roughness, but you can see the distribution is at least peaked in the region, relatively close to what it should be. We can also get scan lines, right? Although we're making an image or measurement of an area, you can take scan lines out, which would be comparable to what you get with a stylus-like device. And one of the customers we're working with has made the argument to his bosses that, look, this device can measure 1,000 scan lines, 1,000 1D profiles instantaneously. So it's as if you had your stylus gauge and you made 1,000 measurements all within a second. And that is an advantage of having a surface measurement rather than just a single 1D measurement. Finally, our alpha prototype of the portable, which I actually I forgot it today. I demoed it last year. Here, this is a device that we're planning to get to beta state, comparable to this, and then release it, have people do testing, early adopter kind of testing for us. Okay, any questions? That brings me to the end of this part, and then I'll fire up the demo. Yep.
That's quite for you.
Okay. Yeah. You have things to look at?
I have a black part which is very difficult to use as a Canadian emission system.
Okay. Yeah, that'd be interesting. Do you know approximate feature size?
What I'm trying to characterize is the radius of this. It's a couple of 100 micrometers radius, so it should be easy to
Okay. Yeah, we could look at it. Yeah, I only brought a simple part here. I need to get a collection of really cool looking parts for GelSight. Eventually we'll get there, but let me just wrap up. So I presented the GelSight system, which is at its core quite simple. We press a piece of gel with a reflective coating onto a surface, and then we can do very fast and easy visualization of the surface and measurement of the surface. So it's fast. It can be high resolution. Of course, for us, high resolution means micron scale. We know that there are devices where high resolution actually means angstrom. So we do need to set the context of what we can and can't measure. And today we're certainly into the microns, but not beyond. And it can be made portable into a handheld device. And we have an alpha prototype like that, which we think is very interesting in the industry in the sense that there are lots of pieces of lab equipment that can make high resolution surface measurements like confocal microscopes, AFM, these kinds of things. And while this has some unique characteristics in that it can be very fast at the scale it operates at, we really do believe that having this kind of resolution in a handheld device is very compelling for the field. Okay, thank you. I'll move on to the demo.
You can just tweak the button here too.
Yep. Okay. Okay, let me first start with what I've got in there since it's already in there. Okay, so as I said, this is beta. We have a couple customers who are using it now, but it's still under under development, very, very active development right now. Let's turn it on. Okay. Oh. You don't really have much screen real estate on this projector. Maybe I can. Nope. Okay. Oh, well, that looks a little distorted though. Okay, well, I think we'll do our best. It looks better on the monitor here. Maybe I can... Yeah, I didn't design my GUI to be used on low-resolution displays, but... Okay, well, let's try it anyway. So... Okay. Maybe I can close that. Okay, so this is actually a coin. You don't have to look all the way in. Under GelSight sensor. I think it's a Japanese coin. And I'll go through the process in a second of how we do it, but it's really a pretty simple system. We've got, this is the core GelSight device. It provides pressure on the gel, and the sample is underneath a piece of gel here. You can apply the pressure by cranking it down, and there's also a quick release that allows us to pick the plate up, swap the sample out, push it back down again. So we've added to this, put this on an XY stage so that you can navigate around, look at different portions of the coin. And this came from some researchers in Japan who really were interested in trying to resolve these features here, these micro-printed letters on the coin, which we can very clearly see, in fact measure. So this uses 6 lights, and we can change the light direction, look at it from different angles. Okay, and once you've decided, what you want to measure, and you've focused and done all those things, we can hit the scan button. And the view doesn't update at this point, but it's taking 6 images, and if you see later, it's just changing the light direction. So it changes the light direction, triggers the camera, does that over and over again. Takes the 6 images, and that's enough to reconstruct the surface. And now we need to get this. I believe it's this one. Yep. Let's say 1, 3. Oops. Uh-oh. Okay. Coin 3. So I went through the process of calibrating the system. I did a quick calibration before. So let's. Okay. So in this view, let me probably kill this. So here's the scan, and once we've determined the calibration, we can just hit the Compute 3D model. And this is an 18 megapixel image, so 5,200 pixels by 3,400 pixels. And it does take a while to do the computation. The program is multi-threaded, but it takes, well, typically on the order of about 30 seconds. So we'll see when it wakes up and comes back. In the meantime, I have some of the scans pre-computed. Temp, set 4x, coin. Oh, let's look at this one. So what it actually computes is the surface normal map. And let's get Photoshop back. Looks like Photoshop. Oh, looks like it went to sleep. Okay. So this is the surface normal map. Oh, my trial expires in 0 days. This one isn't, uh-oh, no. Maybe it'll let me use it. Okay, so here are the surface normals from a section of the coin. And the way to think about this image is we have, it looks like a shaded image. We have the X component of the surface normal stored in the red channel, the Y component stored in the green channel, the blue is the Z component. I can toggle between these to see the different orientations. And if you're not used to looking at this kind of image, which you probably aren't because it's a graphics kind of thing, the thing to notice is, let's see if we can do, wow, it doesn't like this small. The thing to notice is that, in fact, the surface normals are really quite clean. You know, the X component, the Y component, Z component is hard to see because it's mostly primarily flat sample, so it's going to be very close to 1. So that's what the system directly measures, surface normals. But then, as I said, we can integrate those normals to get surface gradients. And for that, to view that, I'm using this, this software by someone I met last year at this conference. Here, also in a trial period on this machine. This machine is sort of just a new demo machine for us. Oops. No. We're going to attempt it in this resolution. Hopefully it doesn't die. Let's go up. Actually, this is interesting. Look at this one first. This is that little printed letter in that coin, this microscale feature that people are interested in seeing. Set the Z-scale to 1. Oops, not used to this. So that's, you know, the surface in this, I think it was on one of these bulbs of that leaf on the coin. Let me actually load it again. Unfortunately, we're really, as I said, we're in beta state, and also some of this third-party software we're using has a hard time with. Sorry, I got to find it. TrueMap. Our measurements are quite a bit bigger than perhaps most or a lot of surface measurements from other systems. I mean, 5200 by 3400 pixels is quite large, and so at this point, well, it usually does load it, but with the error, so we just ignore the error, and then set the Z-scale. So here's a surface map from that coin. Okay.
This is the one you just took. It was finished from this.
Let me see. No, this was a previous. Oh, this one seems to be unfortunately hung up. This is the nature of live demos. Let's let me see what went on. So desktop scans temp set for. Let's rename. Looks like I accidentally renamed it. Typed something wrong. Let's see if we can get it to actually do it. Yeah, it looks like it's going to go this time. Load it from file. So a couple steps when it runs. It has to do the calibration. If it hasn't done the calibration yet, then it takes a number of seconds to actually build the calibration map. It's integrating the surface normals now. That takes some amount of time because, as I said, it is 18 megapixels. It took 20 seconds to solve for all the surface normals. Integration phase took 5 seconds. Saving the file took 0.1 seconds. So we can process the 18 megapixel scan in about 30 seconds on this hardware. It can be faster on an even more powerful computer. So to capture the images, it's about 12 seconds, maybe 1 second exposure, some time between the images, 6 images. So in less than a minute, we've done an 18 megapixel surface measurement. And as you'll see, the workflow can also be fairly fast. There are some little tweaks that we still need to do. So, if you're measuring, if you just want to get different measurements of the same sample, it's as simple as just moving it around, finding where you want to measure, doing another scan, and then hitting the Compute 3D Model button. And it takes 30 seconds. It gives you a 3D model. Let's try some of these. So what do we have? What do we have here?
This you see here is a bunch of 100 micrometer holes.
Okay.
Spaced at 100 micrometers.
Okay. I'm not going to change the gel for now. Mm-hmm. Right up there?
Yeah.
What is this object?
Now whatever I'm checking now is a 100 micrometer microarray holes. And then this is like a regular carbide tip but coated with a backlight kind of a material that's completely black. You can't use other technologies to measure this. I'm trying to see whether this is possible. No, by the jet. Instrument that I'm really careful.
Okay. I passed it, okay.
Yeah.
Wasn't paying attention. Yep. Okay, well we have this coarse adjustment and then interesting. Okay. Let's so we focus just by moving the camera. Okay. So that's that. Let's put that back. View scans. I believe it's probably this one. What do we want to call this? Like just grid or something?
Microgrid, whatever.
So what is the interest in this structure? Just to
We are trying to see whether the circularity is good and the spacing between them are good.
spacing and the circularity?
Yeah.
Okay. I mean, I don't have tools to do
Yeah.
that, but yeah.
I'm just trying to see how much of a shape retention is there.
Yeah.
Because it's close to 100 micrometer deep holes are there. So this is the material flowing into it. So how
It
much-
will flow into it, yeah. But it does. So it does. To this system, every surface is continuous. So there's no. So it's going to integrate through the holes, and it makes sense because, of course, the gel is continuous.
Mm-hmm.
But you could imagine. Okay, it looks like we have a little bit of illumination's not properly modeled, but let's see. Okay. Oh, ignore. Okay. So that's what it looks like. Okay. I suppose at this point you could design algorithms that go in and analyze each of those and determine spacing and so yeah. Okay, let's look at your black part. Okay, so close this.
Is that a gel you could use to test that same part in Oregano so I can get a 3D measurement?
I mean, we can give you the 3D file here.
Oh.
This is a 3D measurement.
Yeah, but I won't have a way of viewing that your data, right?
Yeah, it is in a. Okay, so which side is interesting?
This black edge. So you see that black coating going all the way.
That black coating.
Little bit,
okay.
so it's that edge.
Okay, so we need to. Okay. Let's. Myself a little more room. Okay. So
What is that?
what is what? The
Actually, earlier it was looking like a kind of a dot all around. Then as you kept pressing it, it changed.
well, we don't have a proper mounting system for this, so it's probably pushing it down and it's rolling away. I mean, you could design a mount such that it holds it straight up. We could adjust the pressure though, and maybe.
That's what I was.
Okay. Yeah. Oops. Okay. Let's see if we can. Are the surface features kind of faint like that, or is it?
No, those bubbles should have. The kind of pattern you're seeing is not there. It's actually it should be smooth like that.
What should be smooth?
That area is a curve.
Oh, these. Oh, sorry. These bubbles are probably from the last sample.
Yeah.
Yeah. So I could change gel. This.
I think given a little bit more force, I think it became.
Oh, okay. I mean, it does press in.
Yeah.
Oh, yeah.
That's how it's supposed to look like.
Oh, it's supposed to look like that?
Yeah.
Okay. Okay. Yeah, this particular gel is a polyurethane, which when pressed into something sharp like your previous sample, it will distort the surface, so that's why we have a whole box of gel. Yeah.
Is that what you're expecting to see? I have no idea what looking at.
This is actually a forming tool. So our metal comes like this and then it gets formed on that. So we are looking at the radius of curvature there.
So are all these features?
Supposed to be there.
The cracks are not supposed to be there?
Yeah. It's supposed to be a smooth surface.
Oh, okay.
But since it's black.
Are those actual artifacts on the surface, you think, or is that?
These are definitely on the sample. This might be a piece of lint.
Yeah.
Yeah. I'm
Those
used
things
to.
looks like the surface is scratched.
This is definitely the sample of whatever you brought in.
It's not supposed to be that way, but
I know what I'm looking at. It looked like folds, like somehow this one is gel.
Yeah, I mean, as you can see, because of the gel, even a black part looks the same to the system, right? And so we can new skins. Let's rename just tool.
Putting it to set X assigns it to a calibration.
Yeah, right now. Yeah, that's sort of the way it works. We have one calibration set in here, which I pre-captured, and then I stick it in the same folder. This was tool. Okay.
Yeah.
Yeah.
When do you recommend running that calibration? Is it when you change gel? Is it?
If you change the magnification of the system, if you change the camera exposure parameters,
Okay.
That's pretty much it. Yep. But changing gel is fine if you're using the same type of gel. If the gel gets thicker or if it has a different pigment on it, you need to recalibrate.
They're still looking through it.
Okay, so 30 seconds, and we got that. Let's. So.
I just need to take the data, then I send it through his software to remove all the outliers and make it smooth. Done.
Yeah, yeah.
I just had to go like this one round. And I
So
take his
this-
software to do linearity.
This surface does violate one of the assumptions we're currently making, which is the fact that we're imaging a surface, and this is a distinct part which has discontinuities. So the integration right now is integrating. It's forcing it to be flat, which ends up distorting it. That's something we can remove, but
The solution's already been run, so it's there.
yeah. But yeah, you could see, I mean, certainly a lot of your surface detail, and even with a.
Automatically flipping the data because the curve is happening this way.
I think that's just a result of this boundary, imposing this boundary constraint. However, this software does have the ability to remove these kinds of trends if you're just interested in the surface. You're more interested in the curvature. So
Curvature as well as roughness along the other axis.
So this current algorithm is best for measuring things like roughness. It's not what I would choose to measure coarse curvature. I would do something closer to a Z-stepping or a.
Yeah, you do have choices on how you start that integration. You're not forced to this boundary condition. It looks like it's a flat constraint.
Yes, that's right. So this current implementation in this version does impose that. However, the research code doesn't. So there's, and these are things that we can adjust. But yeah, fundamentally, you can see. So yeah, again, what it's doing is it assumes that everything around this boundary is at the same depth.
Flat surface.
Yeah.
Okay.
Yeah. So. Okay. Anyone else bring any parts? Oh, everyone comes with parts. This is okay. Okay.
Let's just be in serve anybody, just so you know.
Yeah.
I think that's not fair, right?
Well, we can try.
Would you be okay with taking that gel and putting it on some other system too?
You can try. I don't expect it would work automatically, but
Why wouldn't it work?
You want to try it?
if they haven't designed it for the gel, there might be some optical characteristics that.
Yes, there will be a bias because of
Yeah.
I'm not sure. It does sit kind of a little bit angled. I don't know if that's gonna be
So which is interesting?
yeah, the coating.
The coating there.
Yeah, so it's a plasma spray coating that should have a spacing between 40 and 200 microns.
Okay.
Sorry, what is this piece?
This is a femoral stent for hip implants.
All right.
And that's a plasma spray coating, which promotes bony ingrowth.
Stereo integration?
Yep. Yeah, it's not
Hey.
I thought we'd look at it.
Oh, thanks.
I don't know what parameters do you use.
I am a graduate student, and we run a retrievals laboratory at Dartmouth. And
Oh, that looks cool. Yeah, so I did my PhD at Dartmouth. I don't know if you saw that.
It's on the bio.
Yeah.
Yeah.
Is that additive or is that?
It's additive. It's a plasma spray titanium coating.
So this is a really cool looking surface.
Or is that the?
That is the coating.
Okay.
So when there's an
So
osteocyte.
the coating is as atomized as it's.
Yep.
So this actually brings up one of the other properties of the current system, in the sense that when we're imaging at high resolution, we have narrow depth of field. We could combine this with stacking in Z to get extended depth of field. It's not something that this system currently does. So you can see that software, yeah.
Hardware capabilities already built in.
That's right. This is a stacker. But you can see that these are out of focus because they're at a lower depth plane.
But even that's a pretty cool view of it.
Yeah. So let's do a scan and yeah, this is pretty interesting looking coating.
What is the coating system?
It's a plasma spray titanium coating for
metallic titanium.
Yes. Yeah. It is metallic.
Okay, I should be.
That's for
It's for
integration.
osteoconductive. It's an osteoconductive surface for bone to grow into it. So